In this video, we want to write a function that takes an array of sorted integers and a key, or a target, and returns the index of the first occurrence of that target from the array. So as an example here, we have the array A, and note that the entries here are sorted in sequential order, and note also that there are non-distinct entries. That is, there are 2 occurrences of here the number 108, and 3 occurrences here of the number 285. So we want to find what is the first occurrence of the number, in this case the target element that we're trying to find for this array. So for the target being 108, 108 appears in index position 4 and index position 3, but the first of those is here at index position 3. So similarly, if we were to want to search for the target 285, that appears 3 times here. First time in which 285 appears is at index 6. So we would return the index 6. So that's the gist of what we want to solve in this video. And before we go through the main way in which we'll solve it, let's just step through some naive approaches to solving this problem and then see if we can kind of iterate on those and improve based on what we know about binary search from kind of the most naive approach to this problem. So really the first most natural way to solve this problem is to just loop through each element in the array, and then if you stumble upon the target element, that is the first occurrence that you will have stumbled on, because again this is in sorted order, and as you go along you're just, for instance, if we started here -14, -10, 2, 108, that would be the first time that we stumbled on 108, and we would just return that index. So if we found the number 108, we would just immediately return, and otherwise if the number did not exist in the array, we would traverse the entire array and then we would just return something like none to indicate that the number is not present in the list. So it's a pretty straightforward algorithm. Let's just go ahead and code that up very quickly. We'll call that find underscore just to distinguish it from the find function that we will eventually fill out at the bottom. It'll take the same parameters, A, the array, and target, the element that we're looking for. And again, what we're doing is we're just looping through each element in the array. So we're saying for I in range length of A, let's go through that array and then let's check whether or not the ith index of A is equal to target. So if this is equal to the element that we're looking for, just go ahead and return the index at which that element resides. So we'll return I in this case. So if we happen to go through the entire loop without actually hitting anything that equals the target, at the end we'll just return none, and that'll indicate that no such element exists in that list. So this particular approach is one that will work, but it will take linear time to complete, where the size of the array is proportional to the time it takes to actually complete it. So for instance, if we, in the worst case, wanted to find an element that was not present in the list, this would involve us traversing every single element in that list before we found out, oh hey, the element isn't there, and therefore that would take, in the worst case, linear time, or time proportional to the size of the list. So one thing we're going to do in this video, and I'm just going to go ahead and remove this because we're not going to use it in the rest of this video, is that we can apply binary search to make our lives easier to solving this problem. So we can reduce, we'll see that we can reduce the problem from linear, big O of n, to log n, where again n is the size of the array in this case. So binary search, if you saw the video, would deal with an array where we have distinct entries in sorted order. So here we have non-distinct entries in sorted order. So we need to kind of make a bit of a twist of the binary search algorithm that we're familiar with from a previous video to try to help us to solve this variant of the problem. And I just want to note one other approach that we could kind of combine the linear approach and the binary search approach to solving this problem. One way we could do this is we could actually just apply binary search. So the first way that you apply binary search is you kind of define your bounds. You define your low point, your high point, and your midpoint. And let's say that the midpoint, or the point that you find, is the target element that you're after. So let's say that eventually we stumble on our midpoint being this entry 108, which is exactly our target. Then what we could do is we could just, from that target, we can keep going to the left of the array until we hit an element where the left of that element is not the element that we're looking for. So let me just kind of go through this. Let's say we stumble on 108 and we ask ourselves, oh, okay, is the element to the left of this entry also 108? Okay, it is, so that can't possibly be the first entry. And then we ask the same question here at this position. Is the entry to the left of 108 108? Well, no, it's not, so this must be the first position. So this approach will work, But in the worst case, again, you could have an element or an array consisting of all of the same number, and this approach will boil down essentially to giving you the same runtime as the initial naive approach that we came up with, namely a linear approach. So in the worst case, you're still going to get a linear running time algorithm if you just do this kind of binary search approach of finding one of the 108s or one of the target elements and then working forwards or backwards from there, depending on whether or not you want to find the first or last occurrence of such a number. So that's not going to give us the logarithmic time that we're after. So we're going to have to think about how we can tweak binary search in such a way to allow us to get this logarithmic time complexity. So one thing that we can do is we can kind of follow the very similar binary search approach that we're familiar with already. And then what we can do is we can redefine the high point of the array based on whether or not the entry to the left of the one that we're on is the target element or not. So it kind of combines the ideas that we talked about from the previous approach that gave us linear time complexity. But in this case, since we're redefining the high point, we're still condensing the search space in half every time that we do this. So generally what we can do is, let's say we stumble on this 108 here to the right. What we can do is that since we know that the array is sorted and we know that the entry to our left is 108, which is also a target, we can say, okay, well, nothing to the right is anything that we care about because all of the other entries to the right are either going to be 108 or they're going to be bigger than 108. And I don't care about any of those. I only care about the first instance of 108. So I'm going to actually redefine my entire search space to this being the high point and then everything else to the left of it. So we're kind of doing the same elimination tactic that you would generally see in a binary search approach, only we're making a little bit of a tweak to it so that way if we check the element to the left of it, if it's actually also the target, we'll do this redefinition of the high point to tweak our search space appropriately. So everything else though is going to be more or less vanilla binary search. So let's just step through that again because it's good to see binary search a couple times to get it ingrained, and then we'll go over the variant, the twist that we'll be making to give us this this variant that's going to solve this problem here. So much like we do in any binary search approach is we're going to define our low and high. So low is the index of the first element in the array, and then high is going to be length of a minus 1. So that's the last element in the array, but minus 1, so we don't read out of bounds of the array. And then what we're going to do is we're just going to loop while low is equal to less than or equal to high. And then we're going to define our midpoint. So the midpoint can just be defined as low plus high divided by 2. And then what we're going to do is the two if and else if statements that we're going to write now are going to be very familiar to what you would have seen in the binary search video. So basically, if we have an element that we stumble on that's our midpoint, let's say we're here, and this element is greater than the target element, we know that the target element that we're after cannot lie to the right of this element because everything to the right of it is higher than the target element. So we're going to redefine that search space. We're going to eliminate everything to the right of that and redefine this as our new high point. So our high point was previously, let's say here, we've eliminated all of those things to our right, and we've just eliminated that part of the search space that we know can't possibly have the element that we're after. Similarly, if we're, let's say again, here's our midpoint, and let's say the target element is 285 in this case, we know that the element that we're looking for is greater. So none of the elements to our left can be helpful in finding this target element. So we're going to disregard that left portion of the search space in much the same way. So both those statements are going to be identical to what you will be familiar with in binary search. So if A of mid is less than the target, we're going to redefine our low point. So low is going to be equal to mid plus 1, and then else if A of mid is greater than the target, then we're going to redefine our high point, which being equal to mid minus 1. So now what we want to do is we're going to have the scenario where we might have a midpoint that's going to be equal to the target element. And we want to check, again, is this the target element that doesn't have anything to its left that's different than the target element? So for instance, is it a target element that looks like this one here, where the element to the left is not the target, it's 2. So this therefore must be the target element that we're after. So let's do else. And then what we want to do is we want to check if mid A of mid minus 1, if this is not equal to the target, then we know that we found the first element. So if the it's essentially asking, okay, we're here. Is the element to the left of the element that we're on, let's say this element here, if that's not equal to the target, we know we found our first occurrence. So we're going to go ahead and say return mid, because we're returning the index. And actually, before we do this check, we should do another check to make sure that we're not reading outside of the bounds of the array. So we don't want to check a of mid minus 1 and then read an index that's below 0. So we want to do another check here. If mid minus 1 is less than 0, so if this is the case, if we're over here and mid minus 1 is less than 0, then the element that we're on there is going to be the first index of the array. And in this case, since both of these cases failed, then it must be the element that we're after. So if this is the case, we'll also return the middle element. And then finally, what we're going to do, if neither of these two cases are true, then what we're going to want to do, we're going to have a case like this. So we check the element to the left. Oh, no, it's the target element. So again, what we're going to do is we're going to eliminate all the elements to the right of this and redefine our search space. So we're going to set our new high point equal to this guy right here. So that's mid minus 1. So it's pretty much the same thing that we did here. So if neither of these, if those if statements don't, if they don't return the midpoint, then what we're going to do is we're just going to say high is equal to mid minus 1. And that's pretty much it. So let's just go ahead and make sure that this function works as we expect it to. So let's go ahead and say x is equal to find, it's just called find a target. And then what we're going to do is we're just going to print out x. So this is just what the function is returning in this case. So, and actually I guess what I should do is I should also return at the end of this loop here, the while loop, return none if no element is found. So let's go ahead and run this to make sure this actually works. So I'm going to write it, I'm going to clear the terminal, and then I'm going to say Python find first duplicate entry in this case. And the first duplicate entry, again 108, the first entry is at index 3. So that's what we got there, was index 3. So let's just go ahead and make sure that this works for, let's say, 285. So again, if we go up to the example here, we have 285 first occurring at index 6. So let's change our target element from 108 to 285, write that, go ahead and run it, and indeed we get the index of 6. Let's go ahead and try something that's not in there, like 500. We'll see if that gives us none. That does indeed give us none. So that seems to be working as expected. So that pretty much does it for this video. If you have any questions or comments or anything of this sort, please don't hesitate to leave them in the comment section below in this video. The code, as always, will be hosted on my GitHub, and you can go ahead and download that. I'll leave a link to that in the description of this video. Thanks again for watching, and have a great day.